we're now going to take a look at a critically important skill that you will need to use throughout your experience in Chem 2A. It's a method of problem solving known as dimensional analysis. And we're going to introduce this method of problem solving by applying it to foundational problems known as metric conversion problems. We've been working with the metric system in our lectures. You know that metric units are very commonly used, especially in healthcare, and we need to be very comfortable working with them and doing conversions between one type of metric unit and another, or between an English unit, such as weight of somebody in pounds, and being able to convert that body weight into something like kilograms, a metric unit. So before we do these illustrations, I just want to remind you that you needed to have memorized in Chapter 2, Table 2.1, base units of measurements and their symbols. Example, base unit measuring length. The distance between 2 points is the metric unit meter, abbreviated with a lowercase m. Base unit of mass in the metric system would be the gram. Metric unit of volume, measuring the amount of space occupied, would be the liter. So you need to have those symbols and meanings in your tool bag ready to go. Also, critically important, you need to memorize Table 2.5, which lists the metric prefixes. And there's quite a long list. And just to make that more manageable for the things that we are likely to encounter in our course or in the just general field of science as we are a citizen of the planet, I'm asking that you memorize not all of the metric prefixes, but the metric prefixes beginning with mega and going all the way down to nano. And you'll see that listed in Table 2.5. For example, you'll see the metric prefix kilo listed there, symbolized with a lowercase k, and the table explains that the meaning of kilo is 1,000 of whatever base unit it's applied to. We can represent 1,000 either in its standard form or in scientific notation form. So kilometers or kilometers would be referring to 1,000 meters. It is often necessary for us to do English to metric conversions, as I've already alluded to. So I suggest that you memorize these three very common, useful English to metric conversion factors, one for each of the base units that we will be working with very often in chemistry. The first is an English to metric conversion for length. 2.54 centimeters is equivalent to 1 inch. Now it turns out that most English to metric conversion factors, those values are not exact relationships. We just discussed sig figs in the previous video. So this is an unusual exception. 2.54 centimeters equivalent to 1 inch is an exact value. Therefore, sig figs NA means not applicable. Sig figs don't apply. You don't count them here. It's an exact relationship, no uncertainty. The next conversion is a conversion for mass. So 453.6 grams equals 1 pound. That is not an exact relationship. It has uncertainty to it, and as written here, all non-zero numbers. By the way, the 1 would be considered the exact part of this relationship, the uncertainty here with the decimal number, and it has 4 non-zero digits, so 4 sig figs. The last is a volume conversion. 946 milliliters equals 1 quart. And I'm going to squeeze in right here another very common relationship with volume. 1 milliliter equals 1 cubic centimeter, or cc, as they would say it or refer to it in healthcare. So 1 milliliter equals 1 cubic centimeter, or 1 cc. Again, not an exact relationship. For the 946 milliliters equals 1 quart, it has 3 sig figs to it. Okay, now we're going to take a look at how we use this information to write metric conversion factors. And conversion factors are relationships or equalities between two quantities, and they are written as a fraction. So for example, looking at the metric prefix kilo, which we know means 1,000 or 10 to the power of 3. How would we write a conversion factor if we took meters and compared it to kilometers or kilometers? How do you write the equality or the relationship between these two quantities, a meter and a kilometer? You see that right below I have written here in red and emphasized how important this is. When you're writing a metric conversion factor, the first question you have to ask yourself is which one of these physical quantities is the larger quantity. The number 1 goes with the bigger or larger physical quantity. So what is larger, a kilometer or a meter? Well, if kilo means 1,000 of the base unit, then clearly a kilometer has to be the bigger physical quantity when compared to a meter, and the number 1 goes with the kilometer. And now we have to ask, how many of the smaller physical quantity do we need to add up to have an equality with the larger quantity? Well, kilo means 1,000, so literally kilometers is 1,000 meters. We would have to have 1,000 meters assembled to have a distance equal to that of a kilometer. So here is a conversion factor. Again, note the importance. The number 1 goes with the larger physical quantity, which is not necessarily the base unit, as in this example. One other thing that I should mention about conversion factors is that whenever you write one, you should recognize that that conversion factor can be used in its flipped or inverted form if you need to do so in the setup. So this is a true relationship and equality, and I can write it also in its inverted, or flipped form, putting the meter in the numerator, kilometers in the denominator, and then again, the 1,000 meters is equivalent to 1 kilometer. So very important that you recognize that conversion factors can be written in either form, right? You can flip if necessary. Here's another example involving the metric prefix centi. We have memorized that the prefix centi means hundredth, so it is a fraction of, a part of the base unit, smaller than, specifically 1/100th the size of a base unit. And you can write that exponentially or in scientific notation as 10 to the minus 2, or you could express it as 1 times 10 to the minus 2. Either form is correct. So if you have to write a conversion factor involving grams and centigrams, again, you use this principle. Which of these physical quantities is the larger quantity? Well, in this instance, since the prefix centi refers to a fraction of the base unit, the gram unit, the base unit in this example, is the larger physical quantity, and we'll put the number 1 with it. What is the meaning of centi? Hundredth. So how many centigrams would you have to assemble to equal a gram? Well, clearly you would need to have 100 of them. If a centi is 100th of a base unit, then you would have to add up 100 centigrams to equal 1 gram. Similar to the well-known fact that you would have to add up 100 pennies to equal $1 because a penny is 1/100th of a dollar. So you would need to assemble 100 of them to have a monetary value equal to that of a dollar. And one more time, as soon as you write a conversion factor, you need to recognize that that conversion factor can be written in its flipped or inverted form if that is necessary for the solution to a problem. So we can flip it upside down, put centigrams in the numerator, grams in the denominator, make sure we retain the correct pairing of the number with its unit. So 100 centigrams equal to 1 gram, a conversion factor written in two different forms. Okay, let's see if we can't jump in and take a look at how we solve conversion problems using dimensional analysis. So what do we mean when we talk about dimensional analysis? What we mean is that the solution to the problem must be a setup that shows conversion factors written with the correct numbers and units as we've been practicing up above. And this is so important, you must mathematically operate on both the numbers in the setup and their units. And as I've written here, and let's emphasize, the units drive the setup in the problem. You know how to write a conversion factor in its proper form because of the units that are associated with the numbers and needing to operate mathematically on those units. So let's take a look at this first example here, and I've labeled them according to types. So this first example is a metric conversion problem where we're going from a metric base unit to a metric prefix unit, or vice versa. Metric base unit to a metric prefix unit. The example that I've chosen is 24.0 kilometers is equivalent to how many meters? So kilometers involves a base unit going to meters, kilometers involves a prefix, metric prefix unit, and we're now trying to convert to a base unit. So our starting point, of course, is the data that was provided to us, 24.0 kilometers. And we want to convert that into meters. So we're going to have to use a conversion factor. That conversion factor is going to need to have numbers and units in it. We're going to need to operate on both, and the units are going to drive the setup. So what does that mean? I'm going to write a conversion factor here, and the first thing I'm going to do is work with units and put my kilometers in the denominator. Why am I doing that? Because I need to operate on my units. I do not want kilometers appearing in my final answer. I want meters. So I'm putting kilometers in the denominator because mathematically it will cancel with its equivalent in the numerator when you're doing a multiplication division. So the numerator unit will cancel with its equivalency in the denominator. I want to have a final answer of meters. So I have the meter unit now in the numerator, and I see if I stop my problem, my final unit showing will be meters in the numerator, exactly what I'm solving for. So the last thing I need to ask is, what is the equivalency between meters and kilometers? And we just answered that question up above. We know that kilometers is the larger physical quantity, so the number 1 goes with the larger physical quantity. How many meters are equal to 1 kilometer? Prefix kilo means 1,000, so literally 1,000 meters. Therefore, I'm writing the same conversion factor that I wrote above down here. So I see that if I do this calculation, my final unit will be meters, and now I just need to chug through the operation on a calculator, and I think I'm going to have to write here just a little bit more compactly to have enough room. So I'm getting my calculator out. I'm doing the operation, 24.0 multiplied by 1,000. And what do I get when I do this calculation? Well, my calculator is reading this display. And let's just go ahead and put that down here so that we can kind of discuss that reading on the calculator. So 24,000. But how many sig figs does that have? And the answer is, it is unclear. We know we're doing a multiplication division. Our answer can have no more significant digits or significant figures than the smallest number used in the multiplication or division. Evaluating sig figs, I see this number ends in 0 to the right of the decimal point. It is significant. So the 24 kilometers has 3 sig figs. The conversion factor is an exact defined relationship. Exactly defined within the metric system that 1,000 meters is equivalent to 1 kilometer. So sig figs do not apply with the conversion factor. Therefore, our answer should have 3 sig figs according to the only number that has sig figs involved in it in the calculation. So that means, looking at this value, 3 sig figs, the uncertainty is in the hundreds place in this calculation, in our answer, our final answer. So how do I express this number with 3 sig figs? I have no choice but to put it into scientific notation. Starting from where the implied decimal point is, I'm moving over to the left 1, 2, 3, 4 spaces, and I'm going to write down a final answer of 2.40 times 10 to the 4th meters. 2.40 times 10 to the 4th, I've moved that decimal place over 1, 2, 3, 4 spaces. So I have a single non-zero number followed by the decimal place, decimal point, and 2 digits after that for a total of 3 sig figs. So our final answer, 2.40 times 10 to the 4th meters. Let's take a look at our second example, and this falls in the category of converting from a metric prefix to another metric prefix unit. So here is the example that I've selected. 6.7 times 10 to the 4th milliliters is equivalent to how many deciliters? Now, both of these units are metric prefix units. It's very tempting for students at a beginning point in learning how to do metric conversions to want to do this. Just immediately put milliliters in the denominator because we need it to cancel, and deciliters in the numerator. And I want to strongly urge you to resist that approach. Not that it's an invalid approach in terms of use of conversion factors, but it's very tricky for students to get the relationship correct between one prefix unit and another prefix unit until they're very, or unless they're very skilled with the metric system. So here's what I'm going to suggest. It's a surefire way to get it right every time. Two-step it. Take milliliters and convert it into liters. That problem falls in the category of what we just practiced, going from a metric base unit to a prefix unit, or vice versa. Milliliters prefix unit, liters base unit. And then once you have liters, take liters and convert it to the next prefix unit, deciliters. So if I do this calculation, and let me, rather than dirtying my fingers, let's try to dirty this cloth, right? Let's set this up, first of all, converting from milliliters to liters. Looking at my setup, I see that my milliliter units will cancel, and then I'm going to have a second conversion factor where I convert from liters in the denominator to deciliters in the numerator. Now my liters will cancel, numerator and denominator, when I do the second step of the calculation. And I see that I have a final unit of deciliters, which is what I'm asked to solve for. So I'm illustrating here this key aspect of dimensional analysis. You're operating on both numbers and units, and the units are driving the setup. The last thing we need to do is write the equalities, the conversion factors that exist between liters and milliliters and deciliters and liters. So looking at the first conversion factor, once again, which physical quantity is bigger, liters or milliliters? Prefix milli means thousandth. It's a fraction of the base unit. So the liter quantity has to be the larger physical quantity. Prefix milli means thousandth. That means we have to have 1,000 milliliters present to be equal to 1 liter. Moving to the next conversion factor, going through the same process, which is the larger physical quantity, liters or deciliters. Prefix deci means tenth. And how do I know that? That goes right back to table 2.5, memorizing the metric prefixes. So I'm using that information here in these calculations. If you do not memorize the meaning of metric prefixes, you're stuck. You have no way of being able to determine what the correct conversion factor should be in the problem. So deci means tenth. It correlates to dimes. In our monetary system, a dime is a tenth of a dollar. So the liter must be the larger physical quantity. 10 dimes equals $1. Therefore, 10 deciliters must equal 1 liter because the prefix deci means tenth. I now see that I'm going to get an answer with deciliters as my final unit, exactly what I've been asked to solve for. And I'm going to evaluate before I even do the calculation, how many sig figs should my answer have? This first value is a measured value. It has 2 sig figs. Each of the conversion factors are defined exact relationships within the metric system, so sig figs are not applicable. Therefore, my final answer should have 2 sig figs, and I will keep that in mind as I do the calculation. Now notice our given data is in scientific notation. So I'm taking my calculator, I'm entering in the number in scientific notation. I just entered in the 6.7. Now I'm hitting the EE button. Some calculators, it's the EXP button. Some calculators, even a different format. But whatever is necessary for you to tell your calculator, get ready, we're entering in a number in scientific notation. On my calculator, I would not type in the 10. I would simply type in the exponent that 10 is raised to, which in this instance is to the power of 4. So I have entered in the 6.7 times 10 to the 4th. And now I'm getting ready to do this first calculation. I don't take the time to operate on the 1. anything multiplied by 1 is itself. So you don't have to do that part of the calculation. Just divide by 1,000. So I have divided by 1,000. Now I'm going to multiply by 10. And again, no need to divide by 1. Anything divided by 1 is the same value. And I have a number that my calculator is showing me, but before I write it down, I'm going to take the time to go through this calculation twice. So I'm going to double check. 6.7 to the power of 4, exponential 4, divided by 1,000, multiplied by 10. And I get the same answer a second time. Calculator is showing me 670. Make that look a little clearer. But that number should only have 2 significant figures. I can't drop the 0 off because 67 is not the same as 670. Different quantities. I have no choice but to put this into scientific notation, starting from where the implied decimal point is, moving to the left 2 spaces, and my final answer will be 6.7. Let's see if I can't write really small here. 6.7 times 10 to the second deciliters. Our answer showing with 2 sig figs. Let's take a look at a third category or type of problem. And this is where we're converting from a metric unit to an English conversion problem, or metric to English conversion calculation. So in this particular illustration, I'm giving a mass. Mass and weight, by the way, are often used interchangeably. Technically, they are not the same. Mass stays constant regardless of the location of the object to the surface of the earth, but weight will vary depending on whether or not the object is on the surface of the earth or far away from the gravitational pull of the earth. So that is why astronauts experience weightlessness. So we often use them interchangeably. They're technically not the same. In this particular problem, we're taking this mass in pounds, 2.650 pounds, which is an English unit of mass or weight, and converting it into the metric unit, centigrams. So we're going to have to use the English to metric conversion that we memorized up above. 453.6 grams equals 1 pound. Starting the calculation, 2.650 pounds times, and I'm pausing here because I see that this relationship does not have the unit centigram in it. So I recognize I'm going to again have to do a multi-step calculation where I first convert from pounds to grams, and then once I have the gram unit, I can convert to centigrams. So my units are driving the setup. I'm going to put the pound unit in the denominator and the gram unit in the numerator. My pound unit will cancel out, numerator and denominator, in this multiplication division. The equality that we've memorized, 1 pound equivalent to 453.6 grams. And if I stopped my answer right now, I'd have a unit of grams. But that's not what I'm asked to solve for. I'm asked to solve for centigrams. So I need to do another step in the conversion where I put gram units in the denominator, a base unit, and centigram units in the numerator. So I'm back to converting from a base unit to a prefix unit. And what is the relationship between grams and centigrams? Number 1 always goes with the bigger physical quantity. Prefix centi means hundredth, part of, fraction of. So gram, the base unit, is the larger physical quantity. If centi means 100th, then we have to have 100 centigrams present to be equal to 1 gram. Looking at the setup, my gram units are canceling. I'm left with a unit of centigrams in the numerator, which is exactly what I'm asked to solve for. So my setup is telling me, bingo, we're done. All we need to do now is chug through the calculation. On the calculator, double checking. So here we go, making that decimal point and the one here nice and clear. 2.650 times 453.6. Again, I'm not going to divide by the 1. There's no need to carry out the division by 1. Anything divided by 1 is itself. So after I multiply by 453.6, I'm going to multiply again by 100, and I am finished with the calculation. And I'm looking at the number, and then I'm going to clear and run the calculation through one more time to double check that I have not made an accidental error, hit the wrong button on the calculator. Do I get the same answer twice? And I do. Calculator is showing this display, 120204, and I hope that you are checking that as well. Right, so how many sig figs should this answer have? Our data here has 4 sig figs that we started with. This 0 is significant because it comes after a non-zero number and to the right of the decimal point. This second value also has 4 sig figs, and of course, metric to metric conversions are defined exact relationships. So our answer should have 4 sig figs. We'll put a line above the above the 2, fourth digit over. This is the place where uncertainty first begins. Everything else is not reproducible, not part of the significant digits of the measurement. Using rounding rules, we would not round the 2 up. Right, so I am going to convert it now into scientific notation. Implied decimal point here, moving over 1, 2, 3, 4, 5. And I will write down 1.202 times 10 to the 5th. Make sure you don't forget the unit. That's a very common early developmental mistake for students who are beginning their career with chemistry, their experience with chemistry. So one more time here, double checking. 1, 2, 3, 4, 5. We had to move that decimal place to the left 5 spaces to have one non-zero number followed by the decimal point. Looking at the coefficient, I see 4 sig figs, and of course the exponent, 10 to the 5th, takes us back to the original number, 120,204 centigrams, but expressing it now in scientific notation with 4 sig figs.